You know, when we usually look at the heavy machinery that builds our world, we tend to focus on the obvious things, right?
Oh, yeah, absolutely. The massive steel beams, the towering cranes, all that.
Right, the roaring diesel engines. But today we are going on a deep dive into something entirely different, something almost invisible, really.
Hmm.
We are looking at a single technical data sheet for an industrial compound called Jet-Lube EXT FF 1.0.
Which, let's be real, sounds incredibly dry at first.
Oh, totally. I mean, at first glance, a spec sheet for what is essentially an industrial drill collar grease might seem a little mundane to you, but our mission today is to look past the surface. We are going to uncover the extreme science required to keep heavy industry functioning.
Because it's really not just about grease, is it?
Exactly. It turns out the secret to making massive machinery work, it isn't always bigger motors or thicker steel. Sometimes it's a highly engineered, copper-colored paste.
Yeah, and the scale of the engineering dilemmas you face when dealing with drilling rigs operating miles underground is, well, it's almost incomprehensible.
Right. You have tens of thousands of pounds of steel pipe being screwed together, and they're constantly grinding against each other, surrounded by just abrasive rock and mud.
Sounds like a nightmare for any kind of metal.
Oh, it is. They are under crushing hydrostatic pressure. Plus, they're operating at temperatures that would bake a conventional automotive lubricant into a useless powder in minutes.
Wow.
So today, we are exploring how chemistry and physics intersect to manage that unimaginable friction, pressure, and heat. Because without this microscopic layer of chemical engineering, the massive mechanical engineering just completely fails.
Okay, let's unpack this. Because the origin story of this specific compound is fascinating. The source material explains that this Jet-Lube EXT FF 1.0 is actually a modification of an older product.
Right, their standard extreme formula.
Exactly. And the reason they had to alter it comes down to a very specific, almost relatable mechanical problem. Like, imagine you are trying to unscrew a completely rusted, locked-up lug nut on a car tire, but all you have is a tiny 3-inch wrench.
You're not going to get very far. No. You fundamentally lack the leverage to get the job done. And drilling rigs actually face a similar issue on a massive scale. They have these units called rig tongs and iron roughnecks.
Which are basically the giant mechanized wrenches that screw the drill pipes together on the rig floor.
Right. But sometimes those machines simply lack the torque capacity to reach the optimum engagement for these really high torque connections.
You have to picture the physical mechanics of what happens when those iron roughnecks fall short. If the machinery turning the pipe cannot generate enough rotational force to fully tighten the connection, the entire drill string becomes a massive liability.
Because it's literally miles of pipe hanging there.
Exactly. So the engineers at Jet-Lube had to formulate a chemical solution to a mechanical limitation. They designed this specific compound, the EXT FF 1.0, with a deliberately lower coefficient of friction.
So they basically made it extra slippery.
Yes. They chemically altered it to be more slippery, so that those underpowered iron roughnecks could still manage to fully tighten the massive steel joints without needing an expensive equipment upgrade.
But wait, if the machinery itself isn't strong enough to screw these massive pipes together properly, isn't it inherently dangerous to just grease them up more?
How so?
I mean, if you artificially lower the friction that much, how do we know the pipes won't just vibrate apart while they are violently spinning and drilling deep into the earth?
What's fascinating here is the precise balance the chemical engineers had to strike to prevent exactly that catastrophic failure. I mean, it is completely logical to question the safety of making everything slicker.
Right, it feels counterintuitive.
It does. However, the compound isn't just about making things indiscriminately slippery. The technical sheet emphasizes that by lowering the friction, the compound ensures that, quote, full hydraulic joint efficiency is maintained.
Yeah, I saw that phrase. What does hydraulic joint efficiency actually look like in practice?
So it basically means allowing the joint shoulder faces, that's the flat, load-bearing surfaces of the two pipes that meet at the base of the threads, to mate completely flush,
Okay.
without any standoff or deformation. Because, think about it, if there is too much friction in the threads, the machine thinks the pipe is tight because it can't turn it anymore.
But it's actually just stuck.
Exactly.
Right.
That leaves a standoff, which is a microscopic gap. And down in the hole, pressurized drilling fluid can exploit that gap, wash out the connection, and eventually snap the pipe.
Oh, wow.
Or alternatively, if the friction is too high and they force it anyway, the metal threads actually warp and deform.
which is also terrible.
Right. So by lowering the friction just enough, this compound acts as a mechanical equalizer. It compensates for the rig's mechanical limitations, allowing the threads to glide together perfectly until those metal shoulders lock solid.
And once they're locked,
Once they are perfectly flush, the structural integrity of the connection is actually stronger. It vastly reduces the chance of them vibrating apart downhole.
that makes a lot of sense.
Cool.
So you are facilitating a perfect structural fit rather than just making the whole thing loose and wobbly.
Exactly.
So we have a clear picture of why they need it, but the way they measure and apply this compound out in the field leads to the most defining mathematical trait of this entire product. It's right there in the name, FF 1.0.
Yes, the friction factor.
Right. The source states the friction factor of this compound is precisely 1.0 relative to an industry standard known as API RP5A3 Annex I. What exactly is that standard?
Well, the API is the American Petroleum Institute, and they set the rigorous standards for the oil and gas industry. RP5A3 Annex I is their specific, highly controlled laboratory testing protocol for measuring the friction factor of thread compounds.
Okay, so it's a standardized test.
Right. They test the grease under exact, repeatable conditions to determine how it behaves compared to a reference standard. And that 1.0 number dictates everything about how this product is used on the rig.
Yeah, the data sheet specifies that for optimal performance on standard API drill string connections, operators should take the pipe manufacturer's recommended torque value and simply multiply it by 1.0. And it goes further. If they are using premium drill string connections, the highly specialized patented ones with names like High Torque Q, Extreme Torque, XTM, and Delta, those manufacturers actually base their makeup torques exactly on this 1.0 friction factor.
Is that critical?
Yeah. The spec sheet even explicitly warns operators to double-check their premium connection sheet to ensure it shows that 1.0 factor before applying the torque.
Because it is a foundational number for the entire operation.
But I have to point out the mathematical irony here.
Oh, I know what you're saying.
Multiplying a torque value by 1.0 mathematically changes absolutely nothing. If the recommended torque from the pipe manufacturer is 10,000 foot-pounds, and you multiply it by 1.0, you just end up with the exact same number, 10,000.
Yep.
Why is doing zero math proudly touted as a feature on a highly technical engineering document?
Because in a highly volatile, incredibly chaotic environment like a rig floor, predictability is a superpower.
Okay, that's fair.
When an operator is engineering a drilling program, they are managing hundreds of shifting variables simultaneously. By providing a true 1.0 baseline, Jet-Lube is effectively removing a mathematical variable.
Like this, yeah.
Imagine if you use a compound with a friction factor of like 1.15. Suddenly, the rig operators have to calculate adjustments for every single pipe connection. They have to multiply 10,000 by 1.15 and reset the machines to pull 11,500 foot-pounds to avoid under-tightening the joint.
That sounds like a recipe for mistakes.
Exactly. By making the compound exactly 1.0, whatever the pipe manufacturer prints on the spec sheet is exactly what the rig operator sets their machines to pull. It eliminates a massive source of human error.
It's a mathematical anchor in the middle of a storm, but there is a very critical caveat in this source material that we cannot ignore. It explicitly states that this 1.0 is a relative number because the real world is not that sterile API laboratory. The source warns that many factors affect the actual friction factor on the rig.
Oh, the real world is inherently messy. The spec sheet tells operators that while 1.0 is the baseline, real-world experience must dictate the final torque adjustments.
You can't just blindly trust the math.
Right. You have to account for the specific geometry of the threads, slight variations in pipe size, or, most destructively, drilling mud contamination.
Right. If you have a bunch of pulverized rock, sand, and abrasive mud mixed into your connection because you are pulling pipe out of a wet hole, that mathematically perfect 1.0 line shifts dramatically.
It does. And it's a fascinating acknowledgement from the manufacturer. No matter how perfect the chemical engineering is on paper, the sheer brutality of the physical environment still requires human intuition, observation, and experience to make the final call on the rig floor.
Okay, so we've solved the math problem for the engineers on the surface, but all of that perfectly calculated torque means absolutely nothing if the grease itself fails the second it hits the extreme conditions down in the hole.
Very true.
So how does this stuff physically survive? Looking at the product characteristics, the source describes it as using a complex soap thickener with a petroleum fluid base, and it has a distinctive copper color. But here's where it gets really interesting. The spec sheet proudly declares in its bullet points, contains no lead or zinc.
Yeah, and that absence is just as important as what is actually in the formula. Historically, heavy metals like lead and zinc were the cheap, easy way to prevent metal threads from destroying each other under pressure.
Because they're soft.
Exactly. They act as soft, sacrificial metals that just smear across the steel. But they're also terrible for the environment, especially when you're pumping them deep into the earth or washing them off on a rig floor.
Right, you don't want that seeping into groundwater.
No. So the intentional removal of toxic heavy metals shows a massive evolution in industrial chemistry. They're achieving extreme structural protection without relying on legacy toxic elements.
They replaced the heavy metals with advanced chemistry, and the physical numbers on this stuff are staggering. Let's translate some of this jargon for you. The sheet says it has a density of 10.0 pounds per gallon and a specific gravity of 1.21. What does that actually mean for the grease in practice?
Well, specific gravity compares the density of a substance to water, right? And water has a specific gravity of 1.0. So because this compound is 1.21, it is significantly heavier and denser than water.
Okay.
That density is why the spec sheet notes it sticks to completely wet joints and strongly resists water wash-off. When the rig floor is flooded or the pipe is submerged, a lighter grease would just float away and disperse.
You would just wash right off.
Exactly. This dense, heavy paste displaces the water and physically clings to the steel.
And that density also helps it survive what the data sheet calls invert or high pH muds. For context, an invert mud is an emulsion where water is suspended in oil rather than oil in water.
Right.
It's a highly engineered, slippery, and often corrosive drilling fluid that would strip a lesser conventional grease right off the pipe. But this KOPR EXT compound acts as chemical armor. The source even notes it provides superior rust and corrosion protection for up to 6 months while the connections are just sitting out in storage yards.
This raises an important question, though. How does this chemical armor maintain its physical structure when subjected to massive temperature swings?
Good point.
Because viscosity, or how thick a grease is, usually breaks down drastically when you apply heat. The oil separates and it just turns to liquid.
The source actually gives us 2 key metrics for that. First, it states the consistency is NLGI Grade 1, with a penetration at 77 degrees Fahrenheit of 300 and 330.
Which sounds like a lot of numbers.
It does. So to visualize that, NLGI is a scale from the National Lubricating Grease Institute. Grade 1 is roughly the consistency of tomato paste or thick mustard.
Okay, that paints a picture.
Yeah, and the penetration number comes from a test where they drop a weighted metal cone into the grease and measure how many tenths of a millimeter it sinks. 310 to 330 means it's soft enough to brush easily onto the threads, but thick enough that it won't just run off.
But the thermal limits are what truly test that complex soap thickener. You can think of the soap in a grease not as something you wash your hands with, but as a microscopic, three-dimensional sponge.
A chemical sponge.
Right. That chemical sponge holds the lubricating petroleum-based oil in place.
And according to the sheet, that sponge is incredibly resilient. The flash point, which is the temperature where the vapors could potentially ignite, is over 430 degrees Fahrenheit.
Wow.
And its dropping point, the temperature where that microscopic soap sponge literally collapses, allowing the oil to bleed out and drip away as a liquid, is a massive 450 degrees Fahrenheit or 232 degrees Celsius.
And that 450-degree dropping point basically defines its service rating. The spec sheet guarantees that this compound remains chemically stable, maintaining that grade 1 tomato paste consistency from a freezing 0 degrees Fahrenheit, which is minus 18 degrees Celsius, all the way up to that scorching 450-degree mark.
So whether the rig is operating in the freezing tundra of Alaska in the dead of winter, or drilling miles deep into the crust where the ambient temperature of the rock is hundreds of degrees, the physical behavior of the grease remains identical.
Because the ultimate goal is consistent rig floor makeup. If the compound froze solid in winter, the friction would skyrocket.
Right.
If it turned to liquid soup in the summer heat, it wouldn't protect the threads. So by engineering a petroleum and complex soap base that spans a 450-degree operating window, they ensure the mechanical equalizer we talked about earlier performs exactly the same way, regardless of the geographic climate or the depth of the well.
Which brings us to the final, most extreme test. We've talked about underpowered machines on the surface, we've talked about the math paradox, and we've talked about surviving caustic mud in 450-degree heat. But what happens when this perfectly engineered compound is actually deployed downhole? Because once those pipes are thousands of feet deep, the physical stress and the compressive forces they are subjected to are almost unimaginable.
Oh, it is a violently hostile environment.
Huh?
The sheer weight of the type combined with the rotational torque creates immense localized pressure on the steel threads. That is exactly why the datasheet highlights the inclusion of what they call extreme pressure additives, or EP additives.
Okay.
These chemical agents are specifically designed to provide a final layer of protection against seizing and galling under extreme compressive forces.
And galling is a terrifying physical phenomenon. It's what happens when two pieces of metal are pressed together so hard with so much friction that the atomic structure of the metals actually bonds.
Yeah, they become one piece.
They literally weld themselves together. And when the machine tries to force them apart, massive chunks of steel are torn out of the threads.
It ruins the equipment. So to measure how well the compound prevents this galling, engineers use a standardized laboratory setup called the 4-ball weld test.
How does that work?
They take 3 steel balls, clamp them tightly together in a triangle, and press a 4th spinning ball on top of them.
Sounds intense.
It is. They continuously increase the downward pressure on that spinning ball until the heat and friction cause the lubricant to fail, and the 4 balls physically weld into a single chunk of metal.
Ouch.
Yeah. And the source notes that the weld point for this specific compound is a massive 620 kilograms force. It can withstand an immense amount of localized crushing pressure before the chemical barrier breaks and the bare metal surfaces are allowed to touch.
But there is a line hidden near the bottom of this datasheet that almost reads like a typo, and it reveals a totally counterintuitive mechanic.
Oh.
We know it lowers friction to help the machines. We know it has a baseline of 1.0. But the datasheet states that the solids package in the compound is formulated to prevent wear, and then it notes, quote, as stress levels rise above 50% of yield, the friction factor increases, limiting downhole makeup.
Which is wild when you think about it.
It's like the grease has a built-in sensor. It acts as a perfectly smooth 1.0 friction factor lubricant to help the underpowered machines put the pipes together on the surface. But then once it's deep underground, if the rotational forces and the stress levels start squeezing the pipe too hard, it fundamentally changes its behavior.
And we have to define yield to understand why this is so brilliant. Metals have an elastic zone where they can stretch and bend but will bounce back to their original shape.
Right, like a rubber band.
Exactly. But if you push them past their yield strength, they enter the plastic zone, meaning they permanently stretch and deform. The engineers designed the microscopic solids in this compound, the copper flakes and other nonmetallic solids, to actually react to pressure. When the stress hits 50% of the pipe's yield strength, meaning it's halfway to permanent catastrophic damage, those solids physically crush and grind together.
They hit the brakes. The friction factor actively goes up, creating physical resistance that stops the pipe from twisting itself to death. It's a smart braking system made entirely of molecules.
Yes. And if we connect this to the bigger picture, that single nonlinear chemical property is likely saving drilling operations millions of dollars on a regular basis.
How much does a drill string cost?
Millions.
Yeah.
Think about the economic risk. If a drill string is 2 miles underground and the drill bit encounters sudden massive rotational resistance from hard rock, the torque spikes violently. If the lubricant remained completely slippery, that rotational force would just keep driving the threaded connection tighter and tighter until the steel exceeded its yield point, permanently deformed, or simply snapped.
Which would leave half of your multi-million-dollar drill string stuck at the bottom of a hole,
Exactly.
requiring weeks of highly expensive recovery operations.
Right. So by intentionally designing the solids package to increase the friction factor at that critical stress point, the compound acts as an emergency mechanical stop. It physically limits further downhole makeup, preserving the structural integrity of the steel.
That's incredibly clever.
In fact, this protective quality is so reliable that the source details its use in what they call extreme service drilling applications. If downhole makeup or backoff is anticipated to be a major issue, it is actually an accepted practice for operators to increase the standard surface torques all the way up to 70% of the connection's torsional yield, provided reduced tensile capacity isn't a limitation.
So they can crank it way up.
Yes, they can intentionally push the surface machinery incredibly hard, relying entirely on the chemistry to act as a failsafe against equipment failure deep inside the earth.
So what does this all mean? We started today by looking at a single page of technical data, a PDF for what seemed like, basic, everyday industrial grease.
Which turned out to be anything but basic.
Far from it. By digging into the numbers and translating the jargon, we found an incredibly sophisticated narrative. We uncovered a heavy metal-free compound that serves 3 massive hidden roles. First, it's a mechanical equalizer, carefully lowering friction to help underpowered rigs achieve perfect structural joints without microscopic standoffs.
Hmm.
Second, it's a chemical shield, utilizing a complex soap thickener and extreme density to resist caustic invert muds and remain perfectly stable whether it's freezing cold or 450 degrees hot.
Yep.
And third, it is quite literally a smart pressure manager, utilizing a unique solids package to hit the brakes and stop giant steel pipes from permanently yielding and self-destructing under the immense forces of the earth.
It really forces a massive shift in perspective regarding the built environment. I think next time you see a massive piece of infrastructure,
Yeah.
whether you are walking past a skyscraper under construction, driving over a suspension bridge, or looking at a towering drilling rig,
Yeah.
don't just look at the giant steel beams and the massive diesel engines.
Right.
Think about the microscopic, invisible chemical negotiations happening right at the tiny friction points between the steel. Because the reality is, it is those hyper-engineered molecules quietly holding the line against unimaginable forces that actually make the modern world possible.